So we've already covered the product and quotient rules for derivatives and the power rule and sums and differences. The next big important rule for derivatives, and this one is a major deal because it's going to come up in everything that we do for the rest of the year, is the chain rule. And the chain rule is used to take the derivative of compositions of functions. So real quick, we're going to review, from Algebra 2, we're going to review compositions of functions. All right, we've got a chart here that gives some values for x, 1, 2, 3, 4, 5, and then values for f of x, f prime of x, g of x, and g prime. So looking at these four on the right, pause the video, use the chart to evaluate each of these, and then hit play and see if you get the same thing that I do. Okay, so for the first one, g of f of 1, we're evaluating from the inside, so that's going to be g of, and then f of 1 is 3, okay? And then g of 3 is 6. All right, for number 2, we're evaluating f of 4, and f of 4 is 2. Okay, and then f of 2 is 5. All right, for the next one, we have f prime of g of 1, and g of 1 is 5. Okay, and then f prime of 5 is -4. And then lastly, we're doing g prime of, and then first we need f of 4, and we'll square that. So f of 4 is 2. Okay, then we're squaring that. So g prime of 4, which is equal to 1. Okay, so hopefully you got these. Knowing the chain rule, or knowing how to evaluate compositions of functions, is going to be immensely helpful with finding derivatives with the chain rule. Okay, so how do we find derivatives of a composition of functions? So let's say that our function is y equals f of g of x, and we're looking for what y prime is. Okay, first thing I want to cover to get to that is Leibniz notation. I mentioned this in the 2.1 and 2 notes, but Leibniz notation for a derivative is dy over dx, or really what we're looking at is an operation of d over dx applied onto a function y. So this d over dx all together as one expression means derivative with respect to x. And then this says of what? So we're taking the derivative with respect to x of y, or we could write the derivative with respect to x of, and then we could put f of x here or anything else inside there. But d over dx is the operation way to say find the derivative of, okay? So going back to y equals f of g of x. The first thing we're going to do is look at something called U substitution, which is a method to help us kind of simplify our expressions to keep things straight when we're taking derivatives. It's optional for taking derivatives that we use U substitution, but it is mandatory when we are doing antiderivatives, which come later. So it's easier to understand it now than try and learn it when you're trying to go backwards later, okay? So let's say that U represents the expression for g of x. So U is an expression in terms of x. Then Y is going to be f of U. Okay, haha, giggle, giggle, it says fu. Okay, now we're moving on. All right, so it's f of u, and then using this Leibniz notation, we want to find the derivative, so y prime, okay? But what we're actually looking for when we say y prime, since y is originally defined in terms of x, we're looking for dy over dx, all right? But if this expression is now in terms of u, then when we take the derivative of this, we're getting dy over du, the derivative with respect to u. So the question we're asking is, what do we need to multiply that by in order to have dy over dx? Well, not that each of these pieces is like a variable itself, but it kind of makes sense in terms of variables to say if we multiply by du over dx, then these du's will cancel out and we'll be left with a dy over dx. And that same kind of thing works with derivatives actually, okay? So what this means is to take the derivative of y, we're going to take the derivative of the function f with respect to u, but then we also have to multiply that by the derivative of u, which is that inside piece, g of x piece, with respect to x. Okay, so we will end up with an expression in terms of x, but it's going to be a two-step process. We are not taking the derivative of the outside and the inside at the same time. Okay, so here's our the notation that we usually see it. If we have f of u, and remember u is an expression in terms of x, the derivative with respect to x is f prime of u times u prime. In other words, we take the derivative of the outside, leave the inside the same, and then multiply by the derivative of the inside, okay? And you'll probably hear me say that several times. So let's go through a few examples, okay? Now, this first one, because we have a natural log, we have another method for evaluating that. We could split this as the natural log of 5 plus 9 times the natural log of x, and then take the derivative of each of those pieces and get 0 plus 9 times 1 over x, okay? Or we could use a composition, and it doesn't really matter which way you use for this particular function because it's not that one is necessarily more efficient than the other. So let's say that we're not using our log properties and we're just looking at this as a composition. So the outside part, the outer function, is natural log, okay? So natural log of, and this will represent our u, okay? So 5x to the 9th is u, meaning that y is equal to natural log u. Okay, so then when we take the derivative of y with respect to u, we're going to get 1 over u, but then we need, so that's the f prime of u, but then we need to multiply by u prime. And in this case, I'll write it in terms of u first, okay? In this case, u prime is going to be the derivative of this inside. Okay, now we don't leave our answer in terms of u. We have to go back to being in terms of the same variable that we start with, in this case x. So this is going to be 1 over, and then u was 5x to the 9th, times, and then the derivative of 5x to the 9th, which is 45x to the 8th. Okay, in this case, it reduces the 45 and the 5 reduced to a 9, and x to the 8th is gone. So we end up with 9 over x, which is the same thing we would have gotten using the log properties, okay? But here we used the chain rule. All right, if you're ready to try it, go ahead and pause the video and try the next ones. Otherwise, keep watching, okay? So for this one, my outer function, my f of u function is u cubed, okay? So this is u cubed, okay? And this inside piece, tangent x plus 5x, that's u. Okay, so now when I take the derivative of u cubed, I use the power rule, so that's 3u squared times, and I have to multiply by u prime. Okay, so f prime of u is 3u squared and then times u prime, that's not to the first. Now we put things back in terms of x, so we have 3 times this quantity, which is u, so 3 times tangent x plus 5x squared, and then times, now we need to multiply by u prime, which is the derivative of the inside. So that's going to be secant squared x plus 5. Now, in this case, if there were anything to simplify, we would do that. We could square this and then distribute all of that, but it really isn't going to make anything look any nicer, so let's just stop here. Okay, if you want to distribute the 3 to this one, you can, but I would say just stop there. For this one, we do have another log function. I'm going to suggest that we do use one log property first, just to simplify the process of taking the derivative. And that is this square root. I'm going to think of that as a 1/2 exponent, because then I can move the 1/2 to the front. So this is a coefficient 1/2 times natural log of the quantity x cubed minus 7. Now, I still have a composition of functions, so I'm still going to use the chain rule, but I don't have a composition within a composition. I just have basically one level of composition. So this is equal to 1/2 times the natural log of u, all right? And u is this inside expression, x cubed minus 7, okay? So y prime becomes 1/2 times 1 over u. I'm taking the derivative of 1/2 natural log u. 1/2 is just a coefficient, and then times u prime. Okay, putting this back in terms of x, we get 1 over 2 times the quantity x cubed minus 7. So that's the 1/2 and the 1 over u, and then times u prime, which is 3x squared. okay, 3x squared minus 0, because that's the derivative of the inside. I'm going to go ahead and move that over into the numerator. So we get 3x squared over, we can distribute this or leave it factored, it does not matter. So if you'd rather distribute and have 2x cubed minus 14, that is perfectly fine. Okay, for this next one, we have a quotient rule. Now, within the quotient rule, when we take the derivative of the denominator, we are going to have to use the chain rule, okay? So, I'm going to write this as, leaving the 2x there, I'm going to write it as 2x over u, okay? And then let's take the derivative of this, but remember, whenever we take the derivative of the u part, we need to multiply by u prime, okay? So this is going to be y prime equals, so denominator times derivative of numerator, so low times d high, okay? So u times derivative of 2x is 2, minus numerator, top, times derivative of denominator, that's where our u prime comes in, okay? All over u squared, all right? And then putting this back in terms of x, we have x to the fourth, well, I'm going to go ahead and distribute the 2. So I have 2x to the fourth minus 2 cosine x, okay, so that's the 2u, minus, and then 2x times x prime is going to be 2x times 4x cubed, and then the derivative of negative cosine is positive sine, okay, all over that quantity, x to the fourth minus cosine x squared, okay? And then really the only thing left to do, there's nothing that can factor out of the denominator that will cancel with the numerator, but I am going to distribute that negative 2x, which could be done in one step instead of these 2 steps if you want. Move that down. Okay, so we can write this as, we have 2x to the fourth, and this will be minus 8x to the fourth, so that's negative 6x to the fourth, and then minus 2 cosine x, and then distributing that, it's minus 2x sine x all over x to the fourth minus cosine x squared. Again, just leave that like that, don't distribute. Okay? All right, now we've got another one. This is another composition of functions question, but this one is done based on a graph, okay? Now, could we write the equations of this function because they are linear? Yeah, we could write it as a piecewise function, but don't go to that trouble, okay? If you're given a graph, use the graph, okay? Especially if these were curves, don't try and make up a function that would hopefully fit them, all right? Now, we are told that h of x is equal to f of g of x, and we are looking for h prime of 1. So to find h prime of 1, the first thing we want to do is find h prime of x. So that's going to be using a composition that's going to be, okay, so that would be f, call this u. Okay, it's going to be f prime of u times u prime, or putting it back in terms of g, that's going to be f prime of g of x times g prime of x, okay? And now when we plug 1 into that, okay, we have f prime of, and then what is g of 1? Well, g of 1 would be 2 times 1 plus 1, so that's 3. So f prime of 3, okay, times, and then g prime of x. Well, let's put this over to the side here. G prime of x is equal to 2. So it doesn't matter that we're plugging in 1. G prime is a constant, so we can just put times 2. Okay? And then f prime of 3. So this is saying on the graph of f, what is the slope at x equals 3, which is this point right here. Okay? And the slope on this linear segment, we can just count, is down 6 and right 3. So the slope is negative 2. So we have negative 2 times 2, and we get negative 4. Okay, I do want to show you an example, one more example that's not on here. Okay, I want to show you an example of a composition that has a composition within a composition. So I'll just make one up here and then we'll find the derivative. So let's say that we have tangent to the fourth of 7x squared minus 3. Okay. In this case, because we have three functions, we have an inside function that is 7x squared minus 3. The middle function is actually tangent, and then the outermost function is the fourth power. If you want to, if it's a little confusing since this is on the inside, move that to the outside with an extra pair of parentheses or brackets, okay? So now this is the outermost function. If you're writing this in terms of u, you need to keep everything inside the f function, the outermost function, as u. So all of this is equal to u, and y in terms of f and u is going to be, u to the fourth, okay? So then using our chain rule, y prime is 4u cubed times u prime, okay, which is going to be 4 times the quantity tangent of 7x squared minus 3, and that is cubed, times, now we need to take the derivative of tangent of 7x squared minus 3. So I'm just going to pause on this for a second and do that separately, okay? So if u is tangent of 7x squared minus 3, what I can do is I can pick another variable, so I'm going to make it v, and call this part v, so now this is tangent v, okay? And then u prime becomes the derivative of tangent v, which is secant squared v times v prime, okay? And so now I can put this in terms of x into this spot right here where u prime goes. So that's going to be secant squared of 7x squared minus 3, and then times v prime, which is the derivative of the innermost part, which is 14x, okay? And then that all together is our final derivative. I'm going to move the 14x to the front. So we'll have 4 times 14 is 56x times tangent of 7x squared minus 3 cubed times secant squared of 7x squared minus 3.